Okay, so this is actually required practical 3, um, which you usually do in year 12, and you can't actually do the processing of the results properly till you do the rates of reaction topic in year 13. So we're going to determine the activation energy of this reaction here. So we have got sodium thiosulphate, you add acid to it, and what happens is it's actually a disproportionation reaction. You make SO2. You don't see bubbles of SO2 because it's very soluble, dissolved in the water in the solution, and you see it go cloudy because you produce a precipitate of sulfur. Okay, and the way we're going to time how long it takes reaction to occur is a very simple way of doing it. Is here we get a beaker, we draw a cross on a piece of paper underneath, and we time how long it takes for the cross to disappear. Okay, so very quick reaction. The time for it to disappear is going to be very short, and if it's slow, it'll take a long time. Just a word about how, and so we're going to do this, and we're going to do it at different temperatures. So the easy way of doing this is you get a beaker of warm water, or hot water from the kettle or whatever, and then you're going to put your beaker with your thiosulphate in there. So there's your 50 centimeters cubed of thiosulphate in that beaker, and you put a thermometer in there, and you wait until it reaches the kind of temperature that you want it to be, 50 degrees C or whatever, and then you take the beaker out. I'll go to there. You start the reaction by you add 5 centimeters cubed of HCl. So you've got to add HCl. So 5 centimeters cubed of HCl, concentration 1 mole per decimeter cubed. Put that in, start the clock, time how long it takes. Now, of course, you're going to end up with, so you're going to have to record 2 temperatures. One, the start temperature, and secondly, the final temperature. Now, the start temperature will be when you take it out of this beaker here. So that will say be 50 degrees C. But then you will have added some HCl. Now the HCl here, that you haven't warmed that up in the water bath, so that will cool it down a little bit. And also when you're waiting for the cross to disappear, it's not in the water bath, so that will cool down. So it may have gone down to say 46. And the usual thing to do is just say at the temperature there is going to be 48 degrees C, the average. Okay, so that's how you change the temperature. Now here's some results. Okay, so you can see there that the temperature as it goes up, the time for the cross to disappear gets shorter. Right, there's one dodgy result there. I'll just leave it in there. That one at 45, it seems to be out of sequence as the others, but we'll just leave it and we'll plot it on our graph, and it'll be obvious that it's an anomaly. How do we process the results then? Well, first of all, let's think about the Arrhenius equation. Now, the Arrhenius equation, you're going to get Ln rate is equal to a constant, Ln A, minus EA over R 1 over T. Strictly speaking, that should be Ln K. Well, K is the rate constant, but Ln rate is proportional to Ln K as long as you keep the concentrations of everything the same. I explained that in a previous video, so we're just going to do rate, okay? So we want to end up plotting, we're going to fit that into our straight line graph. Y is equal to mx plus c. So that's c, and we're not really interested in c. We're not even going to plot it down to the origin of the graph. But we want to plot Ln rate on the y-axis, and on the x-axis we want to plot 1 over T, but T's got to be in kelvins, okay? So the first thing we've got to do is we need to convert degrees C to Kelvin. And that is easy enough. We'll just add 273. The next thing we need to do is we need to think about the rate. Now, we haven't got a rate here. We've got the time taken for the cross to disappear. But we know that rate Do that in red. We know that rate is proportional to 1 over the time taken. So we want to work out rate. We're just going to use rate as 1 divided by the time. So for example, for this one at 50 seconds, it'd be 1 over 30, but that's a bit awkward because that's going to give us like a number smaller than 1, which is just, it's not a problem, but it's a bit awkward. So it's a bit easier if you just turn that into 1000 over time. It could be any number at all you like. It could be 50 or whatever, but 1000 is easy. That's what we're going to do. So rate is 1000 over time. So for that one, rate would be 33.3, and it wouldn't have any units. But it doesn't matter, it doesn't have any units because we're going to take a log of it, a natural log of it anyway, so the units are going to disappear. Okay, so that's what we're going to do. We're going to plot that graph then, when we've worked out those values, and we know then the gradient of that graph is going to be minus the activation energy over R, the universal gas constant. We know the universal gas constant, so we can work out the activation energy for the reaction. Okay, so let's have a look at a list of those process results then. Well, that's spoiling the surprise. Okay, so there is our list of process results. So here we've got our temperatures in degrees C. We've converted them into kelvins. This is the time taken for the cross to disappear in seconds. This is the rate. We've done 1000 over the time taken, so you can see you can see that as the time gets shorter, the rate of reaction increases. Okay, then we've taken a natural log of that by just pressing the Lun button on our calculator, and then here we've done 1 over the absolute temperature. And don't forget, look, they're all like, it's going to be, so you're doing 1 over 293. It's going to be quite a small number. It's going to be 0.00341. So don't forget, we've got the 10 to the minus 3 bit there. Now we've got to plot these on a graph. I tell you another good reason for doing it. If you do 1000, we've done 1000 over time here, yeah. It means that all of these rates are all bigger than 1, and that tends to mean that when you do a Lun value of it, it's not negative. Otherwise it'll be negative. Again, it's not a problem, but it's just another thing to make a mistake. It's easier working with positive numbers. Right, let's have a look at the graph if we plotted it then. Okay, so there is our graph. So let's make that a tiny bit smaller. Okay, so we've got we plotted Lun rate on the y-axis, and we plotted 1 over the absolute temperature on the x-axis. There's our line of best fit in green, and then we have to work out the gradient of that. Now the gradient is equal to the change in y over the change in x, and I would definitely recommend don't just do it in your head or on your calculator. Draw the construction lines like I've drawn here. So look, I've drawn the triangle, and then I've worked out delta, the change in y, 2.5 minus 3.25, and it's a negative value, look, because you've got a negative slope to this graph. The change in x, we've got that value there. So we want to work out the gradient is, there we go, minus 0.75 over that, which is equal to 3947.4. Now we have to work out activation energy. Now we remember that the gradient m is equal to minus EA over R, which is R is the gas constant. R is given us as a value of 3.1, and the units are important here, joule per mole per Kelvin. That's joules, it's not kilojoules. So let's rearrange this equation to give us the activation energy. EA is equal to minus R times the gradient, 8.31, multiplied by the gradient we've got is 3947.4, and that is going to give us that's give us 32802.9. Right, so we need to get a that's, and the units of that's what the units are going to be. They're going to be joules, because let's think the units of EA, right? Oh, we've got EA here. The units of that are joules per mole per Kelvin. The units of the gradient, if you look at the gradient, well, look, it's changing Y. Y doesn't have any units because it's a log value, but X has got a value of kelvins to the -1. So that's divided by kelvins to the -1. So the two lots of kelvins are going to disappear. So the units here are going to be joules per mole. Let's convert that to kilojoules and put it to the correct number of significant figures. They will have 3 significant figures. So we're going to get a value of 32.8 kilojoules per mole. That's the activation energy of that reaction between hydrogen ions and the thiosulphate ions. Okay, so that is required practical 3. It's also practicing working out activation energy from Arrhenius, using the Arrhenius equation. And I can't stress how careful, when you plot these graphs, be really careful. Plotting a graph is not like a top level skill. You know, you've been doing them for years. Working out a gradient, that's not really a top level skill. We've been doing that since year 10 in maths. But there's just so many things to go wrong there, because it's not terribly hard. People are a bit careless, and people always make loads of mistakes in these questions. You know, people are really good at chemistry and good at maths, and they end up messing them up because they're just a bit careless. So be really careful. Write down all of these, all the intermediate steps, draw the construction lines, and so on.